Hello everybody and welcome to our video today where we are talking about physics, chapter 7, light and sound waves. So there's a couple things to cover in this chapter, so let's get right into it. We have Hooke's law, which is equal to, which is F equals negative kx. And this is for harmonic motion for springs, okay? So we have F equals the restoring force, where K is the spring constant and X is the displacement from equilibrium. So this is just a visual. So this is our spring and our mass, for example, and this is at equilibrium, X equals 0. So if you're compressing the spring that way, or you're pulling the spring this way, you're moving, right? There's a displacement from equilibrium. So that's the most important part to understand here, as well as this equation. And so the amplitude is the greatest distance from equilibrium. So if I pull it all the way here or compress it all the way that I can, that's the amplitude. Then we have the period, which is the time it takes to complete one cycle. So with springs, it is independent of the amplitude. Like period is independent of the amplitude. Therefore, there's a constant, the period will be a constant time, no matter the amplitude, okay? Frequency is the number of cycles per second. So F equals 1 over the period. And in springs, it's actually 1 over 2 pi times the root of K over M. So you can see we're using the spring constant and the mass. Another important equation in this chapter is PE elastic equals half of kx squared. So this is the potential energy, right, which is the energy stored in the spring, equals 1/2 of kx squared. And the work done by the spring equals the change in PE elastic, so the potential energy of the elastic, because spring force is conservative. That is important to note for the spring, okay? And this is different, if in the case if we're using like a bouncy ball, right? But for springs, spring force is conservative. And this is also another equation. So we have the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the potential final energy. And that is important because when you're compressing the spring, right, all of it is potential energy. Or when you're pulling it the other way, all of that is potential energy. But as soon as you let go and it's actually moving, now that potential energy has been converted into kinetic energy. So this is that equation. And then I'm hoping you can see this. I'll bring it down for a second to make sure that you can. And we also have Vmax down there. It says Vmax equals the root of K over M times the amplitude. And that is just saying that the speed is proportional to the amplitude. Okay, so speed is proportional to the amplitude. Next, we are going to talk about pendulums. So the important part here is to know that the displacement is in radians, okay? So here's just a figure. So we have this pendulum that has a mass of m. The L is actually the length of this right here, and then theta is this angle right here between equilibrium and the pendulum. So the equation for frequency for a pendulum is F equals 1 over 2 pi times the root of gravity over L. So it is not dependent on mass, but it is dependent on gravity. And then we have the force, the restored, equals mg sine theta, okay? And then we have the period, which is 1 over f, equals 2 pi root length over g. So this, again, personally, I have not seen this as much in any of the practice things that I've done. However, I'm sure it's still an important concept. And I know with all these equations, it can be a little confusing. So I would definitely suggest just writing them out, seeing how much you can get from this video, and then following up with other, other YouTube videos, other Khan Academy videos, anything like that, to understand more of all of these specific concepts, because this is just a general overview of the content to make sure that, we're really covering all of it. Let me just see if there's anything else to be said here. No. All right. So moving on, we have waves. They can either be, they're transverse waves and they're longitudinal waves. So a transverse wave, as you see here, which I'm hoping you can see. Okay, that's an example. The transverse wave, a good example is light, while a longitudinal wave, a good example is sound. So you can just see the difference in those waves. Now, next we have wave speed. So the speed equals the wavelength times frequency, okay? And this is the unit. So we have meters times 1/seconds, which equals meters per second. So that's why we have the speed in meters per second. So the speed of a wave is dependent on the medium that is passing through, and another important thing is that frequency is constant as you're going from one medium to another. So that's just an important note there. And then we have constructive interference with our waves and destructive interference. So constructive interference is when the waves are in phase, right? And that means the amplitude equals the amplitude 1 plus amplitude 2. So it's going to be larger when you have a constructive interference. But if you have a destructive interference, the waves are going to be out of phase, and it's going to, the amplitude is going to be smaller. But the amplitude equals the absolute value of amplitude 1 minus amplitude 2. And finally, we have beats, okay? And beats actually have both kinds of interference because you can see them overlap at different points along the wavelength. And so for beats, we're going to use FB equals the absolute value of F1 minus F2, because both of the interference types can be present. Next, we have intensity. So this is a good application for sound waves. We have the intensity equals power over area, which is equal to watts over meters squared. And that again is just, I believe we have a couple of examples coming up, but the equation is important, and to know that this is an application of sound waves, and as well as its power over area, in case they just, give you those two things. And then we have, for a spherical wave, the intensity is proportional to 1/r squared. Therefore, the intensity is proportional to the amplitude squared. So that's for spherical waves, just another, subset of this intensity topic. But yeah, definitely just know this equation. I'm just going to switch out the boards here. We have another board to get through. Okay, so this next part, we have standing waves. And we're looking at these standing waves, for example, in a pipe that is open at one end. So we have Fn equals Nf1. Okay, so frequency, and I'll explain what these n's are in a moment. And then the wavelength equals 2L over N. So if we have the first harmonic is going to be N equals 1. Here, this is what it looks like. Okay, here, this is what's called a node. And this is the length. If we're using this equation here, that means we're going to have wavelength equals 2L, right? Because it's going to be 2L over N, and N is 1, so it's going to be 2L over 1. So wavelength is going to be 2L for first harmonic. Then we have our second harmonic, which we see has a node and a node here as well. Okay, and this is the length of our second harmonic. And here we're going to have wavelength equals L, because it will be wavelength equals 2 times L over 2. So the 2's would cancel out and you'd be left with wavelength equals L for a second harmonic. And then for the third harmonic, we have N equals 3. Again, this is the length. And then that means that L would be 3 wavelengths over 2. Because again, we are using this equation. Here we are just rearranging the equations. If we were looking at just the wavelength for the third harmonic, we would just have 2L over 3, right? Because it's N equals 3 in the third harmonic. But if you were, what's the word I'm looking for? If you were just solving for L in this case, you would get 3 lambda over 2L. So hopefully that is a little bit more clear now. And yeah, and everything you see drawn here is just rearranging it. Wavelength and L, just using this equation. So this is just a visual representation of this equation so you can better understand with the first, second, and third harmonics. Moving on, we have decibel levels. Okay, and this equation looks a little complex, but we'll break it down so we can show you an easy application of this. So here you have beta equals 10 log base 10 intensity over initial intensity. Okay, so first thing is we're going to say that the B is decibels. And then again, just simplifying this a little bit more, we have the initial, intensity naught, right, equals 10 to the negative 12 W over M squared, which is the threshold of hearing. So these equations, like I said, are a little complicated to grasp, but the important part is the application of it. So because we're dealing with logs, if we're increasing the intensity by a factor of 10, we're going to add 10 to B. Okay, and what I mean by that, for example, is if we're increasing intensity by a factor of 100, we'd have intensity times 100. This 100 can be broken down into 10 times 10, right? And then times I. So it's going to be 100 intensity equals 10 times 10 times intensity, right? And with that, when we were talking about above adding to B, that just means as the intensity increases, you're going to add to decibels, right? And you're going to add 20 because you're going to do 10 plus 10. So it's going to be whatever the decibels were plus 20 decibels if you're increasing by a factor of 100. So hopefully this example, was clear. Again, this is a pretty common example actually. So I would definitely just understand how this works and how you can break this down into something, just kind of look at it a little more simply. And then finally we have the Doppler effect. So if we have the detector moving closer to the source, the frequency is going to appear higher. And I say appear because it's, technically not. However, it's going to be portrayed as a higher frequency. And then if we have the detector that is moving away from a source, we have a lower frequency that is perceived. And there is an equation that goes with this. This is the equation. I think the important part is conceptually knowing that, for example, if you're the biggest example of the Doppler shift is if you're standing on the street and you hear a car going by you, right? It might start out low and be like, right? So as soon as it gets close to you, it seems like it's a much higher frequency than if it was further away. And even though the frequency doesn't change, because the detector, you, and the source, the car, are getting closer, the frequency will appear or will be perceived as higher. So that's just the application of the Doppler shift. So this brings us to the end of our video. If you have any questions, please put them below in the comments, and otherwise I'll see you in the next video.